Well, hello C++ programmers, Brian Malloy here. In today's video, I'm going to try to differentiate between lvalues, rvalues, lvalue references, and rvalue references. And why do we want to do that? We want to do that because we are moving into that area of C++ that uses move semantics. So let's just read a few things. I think this is a great reference for move semantics. This is Effective Modern C++, Scott Myers. And what he says right here, move semantics can help you to avoid expensive copies by simply doing less expensive moves, which is an optimization. So as I've said before, the rule of 3 can help keep your program from crashing. The rule of 5 can help keep your program from using expensive copies and replacing them with moves. Okay, so how do we avoid these copies? We use a move constructor and a move assignment operator. And how do we know when we're using those? Well, if the signature has an rvalue reference. This is kind of a pattern, for an rvalue reference. Okay, so what we want to understand in this video is what makes for an rvalue reference and what are the other things. So before I go into that, let me just say something that Scott Myers is very clear about. We're going to be using in this video std move. And what I want you to understand is that std moves nothing, absolutely nothing. It doesn't move a thing. And in fact, Scott Myers says he thinks they should have called it something like rvalue reference cast or something like that. You can read these items. He has what he thinks it would have been more descriptive. I don't know why they used std move. I guess because rvalue references are needed in move semantics. I guess that's why they called it that. I don't know. But what std move says, so if you have std move of x, what you're telling the compiler, look, I know you think x is an L value or something. I want you to consider it an R value so that it can go match an R value reference. Okay, that's the one thing I wanted to point out. And also, as Scott Myers says, perfect forwarding is not perfect. Really, we're not going to talk much about perfect forwarding, but really all perfect forwarding is telling the compiler, look, this parameter came in as an rvalue reference. I want it to go out as an rvalue reference. Now, we're not going to be going into that very much, so I just thought I'd mention it. But that's perfect forwarding in a nutshell. And it's not perfect because, you shouldn't even have to do it probably, I guess. But anyway, let's go ahead and get out of this and start talking about L values and R values. So, a long, long time ago, after the music died, but before C++ 11, all programmers we needed to talk about were L values and R values. Life was simple. Elvis was king. We'd go down to the levee in our Chevy and be happy. However, C++ 11 came along and they decided they would designate move semantics with R value references. So now we have to be able to differentiate what they mean. Okay, so what were L values and R value references and still are? It's very easy. An L value is any object that can appear on the left-hand side of an assignment operator. An R value is really anything else. Or an R value is something that can only appear on the right-hand side of an assignment statement. So let me just give you a little example. Int x. Let me put x and y. We have int x and y. I can say x equals 9. And x is clearly an L value there because it's on the left-hand side of an assignment. But I can also say y equals x. Wait, let me space this a little bit. And x is being used as an R value, but it's actually an L value because even though it's not appearing on the left-hand side, it could. So if an object can appear on the left-hand side of an assignment operator, then it's an L value. Scott Myers has a better, more modern definition of an L value. He says it's any object for whom you can take its address. So for example, we can say int star p is equal to the address of x. And here, clearly, x is an L value because I'm taking its address. Okay, so that in a nutshell is L value versus R value. Let me just add a few other things. I can never say 29 equals x. So clearly, 29 can never be an L value. That won't compile. Or 3 plus 4 equals y. That won't compile. So 3 plus 4, why? Because 3 plus 4 has to appear on the right-hand side of an assignment statement. So 3 plus 4 is obviously an R value. And we're going to see examples of that in a moment. So I have here a little program that I've written to try to delineate L values and R values and R value references. So let's take a look. Int x equals 0. Clearly, x is an L value because I can take its address. And if I call f of x, I'm going to get this right here. This is actually an L value reference. Why don't we call it an L value ref? We might as well call it that. Let's call it what it is. Okay, what am I doing? Okay, so let's move this all over so it's, oh, I'll quit there. Okay, so if I call f of x, I'm going to get L value reference. Why? Because x is an L value and I pass it in here by reference. So it's an L value reference. Then I say f std move of x. Okay, well, what we're saying to the compiler, look, you think x is an L value but right here, but I'm telling you it's not. Don't even think of it as an L value. Think of it as an R value. So we're going to match this signature. And that's what this is all about. How do we match signatures? In fact, given what you know, this kind of looks like the signature for a copy constructor, and this is a move constructor maybe. Okay, so that's what we're moving toward. I'm sorry, that's what we're aiming for. I don't want to I want to try to disambiguate my terminology here. So what are we going to get? Here we're going to get L value reference because it's an L value that comes up here and it becomes a reference to it. Here we're going to get R value reference. Clearly this is an L value. It can never appear on the left-hand side of an assignment statement. You cannot say x plus 1 equals anything. So that's an R value and it's going to match this signature and become an R value reference. Similarly, f of x, here's f. Here's f defined. We're going to return 7. And what's going to happen there, this is a real important example in a way, because when we return 7, the compiler generates a temporary to hold that 7. And that temporary, compiler-generated temporary, is going to come back here and get passed again into, actually, where's that going to go? It's going to go up here. It's going to go up here, R value reference, because compiler-generated temporaries are always R values, okay? And those are very, very excellent candidates for move semantics, because what had happened prior to C++11 is when the compiler generated a temporary, it would come back and then get copied in its next use, most likely. I'll try to show you an example of this in the next video. And so that's what we want to avoid. We want to do a move instead of a copy. So let me go ahead and run this, and let me predict the output. We're going to get L value ref, R value ref, R value ref, R value ref. So let me just go ahead. Hope this compiles. It does. It's giving me a warning because I don't use P. And now if I run it, we get L value ref, and all of these are, let me show you. So we're getting L value ref here. It's matching that signature, which we've seen already before. It's this one that's new. And I'm trying to help you to get used to this. This is just notation for R value reference. Okay, so now clearly we've already talked about what move means. So that's going to match that signature. This one's going to match that signature. And this one's going to match that signature. If you can follow that, you are halfway, you've made 50% of your progress toward understanding move semantics. Well, maybe 25%. I don't know. But you certainly know how the signatures get matched up at this point. Okay, so we'll move on to move semantics next. Oh my goodness, I got to stop saying move. Hey, happy programming. Brian Malloy, over and out.